sure you will not be the same at the end of this session. Over to you, Professor Taiwo.
Good morning, Dr. Lawal. Good morning, everyone. It's always my pleasure to be with you to share some insights concerning research methodology. This morning, like Dr. Lawal said, we'll be talking about quantitative data analysis, and that's the first part, hoping that by God's grace next week we'll look at the second part. I always like starting my presentations in research methodology with this research process. It helps to situate the topic, depending on whichever area we are talking about. So normally you start your research with a question, something that you are thinking about, you go and check your literature review, you have an hypothesis based on what you find out there, you determine your hypothesis, and then you talk about the particular approach you intend to do or use in answering your research questions. You sample your data, you have your sampling method, and then you talk about the variables that you are going to be measuring. The variables you measure will give you your data, and once you have your data, you analyze. So invariably, this is the area that we are talking about with much emphasis on the data analysis. So let's quickly talk about variables. I believe by now you have an idea of what a variable is. A variable is a characteristic that may assume more than one set of values to which you can at least give a numerical measurement. A variable is a characteristic that may assume more than one set of values to which a numerical measure can be assigned. It's a characteristic that can change, unlike a constant which does not change. And for variables, we actually have two types of variables. We have the quantitative variables, and then we have the qualitative variables. The quantitative variables are also divided into two. We have the continuous variables and discrete variables. So just for a brief reminder, anything that you can measure is a continuous variable. Anything that you can measure, anything that can assume a decimal point, like height, like weight, like pressure, like temperature, anything that you can measure is continuous. Whereas whatever is whole number is discrete, like the number of people presently on the online now for this class. It's a discrete. We don't have 11.3 people. We have a discrete number. And for the qualitative, whatever you can arrange, either by ascending order or by descending order, is called an ordinal variable. Like maybe educational level. You have maybe primary, secondary, and tertiary, or none. That can be arranged by a kind of ascending or descending order, or a Likert scale. Many of us have heard of Likert scale, where you have strongly disagree, neutral, agree, strongly agree. It can either go on an ascending order or a descending order, or like the stages in pregnancy, first trimester, second trimester, third trimester. All of those are ordinal variables. And then we have the nominal variables that are just labeled, like yes and no, like colors, blue and black, green, yellow, red. All those ones are just labels. They can't be arranged in any natural order. Now, variables, when they are measured, gives you data. Logically, the kind of data will also follow the kind of variables. So for data also, we have quantitative or numeric data. That's another name for data, for quantitative data, or qualitative or categorical data. And like I said, they still follow the same classification like we have for variables. So we have continuous data, discrete data, and that is under qualitative. We have nominal data and ordinal data. Remember that data, it's variables that you have measured. You are given a numeric value. So this is an example of a data. We just have like 6 people and their weight, 25 kilogram, 33 kilogram, down to 22 kilogram. That's just data. Information is a data that has been processed. From these 6 people, we can say that 4 people are in the 25 to 30 kilogram group. 2 are above 30 kilogram, okay, 30 or 30 and above. And in statistics, we already have further processed that data to give us the mean, median, and a standard deviation. So you can see how data differs from information and statistics. So like I said, data are raw facts or figures from where inferences can be made and conclusions drawn. They are quantitative or qualitative. They can be either of the two. Information, like I said, is data that has been processed. so that it's more meaningful to the audience or reader. Like the previous slide I showed us, we have about 4 people, in a particular range of weight. Statistics is the science of data collection and analysis. It refers to information obtained by mathematical operations. So that's where statistics come in, excuse me. By mathematical operation, on numeric data. By mathematical operations on numeric data. That is why we can perform statistics, as it were, in qualitative research designs, because most of those data are what? Figures, and maybe pictures. They are not numerical. So for data analysis as a whole is the process of transforming crude data into information or statistics where you can now make decisions. And there are 2 types of or 2 approaches to quantitative data analysis. It can be descriptive or inferential. Descriptive or inferential. The descriptive is the part 1 of what we're talking about today. Inferential will be part 2, and we'll be looking at that next week. So the descriptive, they refer to information that summarizes or organizes. Please look at those keywords. Summarizes or organizes the basic features of a data set. For the inferential statistics, here the information that you get from the data is used to make inferences, 1, suggestions, 2, or draw conclusions about other entities similar to, but not the ones from which the data was obtained originally. And it can also be from the one the data was obtained from originally. That is when you are inferring back to the population. So don't let us just knock out the population from where our data was gotten from. So the inferential statistics uses sample data to draw conclusions and make predictions. That's another keyword there, predictions about a larger population. So it's just to generalize findings to a broader context. Let me go over that inferential statistics. Here, the data that you have, you use it to make inferences, suggestions, predictions, or you draw conclusions about other entities that can be maybe the larger population from where your data was drawn from, or other entities from where your data was not obtained originally. We need to understand the differences. So when we do quantitative data analysis, it normally follows a strategy. That is, if you are working with just 1 variable, or 2 variables, or more than 2 variables. 1 variable here means the univariate. 2 variables by variate, multivariate means more than 2 variables. So let's recall that example I showed us earlier on about the weight of 6 people. That will be a univariate, because it's just talking about weight. You understand? We can now calculate, do anything we want to do about our weight. But let's assume we are trying to look at the relationship between maybe weight and then the height of the 6 people. Now we have 2 variables, and we have a different strategy when you're looking at analysis involving more than 2 variables. Now, if it is weight, height, and maybe the temperature, it's more than 2. There's another strategy for analyzing that kind of data, And interestingly, the univariate variable most of the time is descriptive. Sorry, I don't know what's happening to my cursor. The univariate variable is most of the time descriptive, while these remaining 2 are most of the time inferential. I just wanted to understand that difference. So like I said earlier on, descriptive statistics, in short, is for organizing your data, summarizing your data. Please don't forget that too, organizing and summarizing your data. You are just describing what you have gathered from your research, from your data collection. So for the univariate, which I said is more like descriptive, it can be categorized into the quantitative variable and then the qualitative variable. For the quantitative variable, we can do a measure of central tendency, we can do variation, variation is a measure of dispersion. We'll talk about that as we continue. We can check the distribution of the data, and there are some plots that can be used to describe, or to organize the data. For the categorical, we normally have frequency and plots. Nearly all of this that we are seeing here are things we are going to talk about very briefly in this presentation. So for central tendency, we have mean, median, and mode. For measures of dispersion, which is also called variation, we have variance, standard deviation range, percentiles, and interquartile range. For the distribution, it can be normal, it can be uniform, it can be exponential. For the plots, we have histogram, box plot, stem plot, dot plot, line chart, time series plot. And for the categorical variable, we have count, where you have a table, frequencies, percentages, and the odds. And for the plot, we have the bar graph, pie graph, and Pareto graph. We are now going to be talking about the odds in this presentation. So let's quickly look at descriptive statistics is used by researchers to report on populations and samples. Populations and sample, and the purpose is to describe the data that you have. By summarizing information, descriptive statistics can help you speed up and simplify comprehension of the characteristics or the data set. Inferential statistics, on the other side, allows researchers to make decisions or inferences or predictions or draw conclusions by interpreting the data patterns that you have seen. And that will be coming up next week. So we have the population, and most of our study is based on samples that you must have drawn out of the population. So this is basically what we describe, and it is still the same sample data that we work on to now infer on what could have been happening in the population. That's what inferential statistics. Okay. So we want to describe the samples and populations if it happens that you are working on the whole populations. And describing population is a matter of inference because, like I said, most of our studies are based on samples. Most of them are based on samples. So you are using the sample to make predictions, to make decisions, or to run conclusions concerning the population from where they were gotten from, or similar populations from which similar to their source data. Look at this example. We have a class here of 13 students, class A, and there's another class B, both of them with 13 students. And this is the weight of each of the students there. And there's a simple question here which says, which group is heavier? We have 13 measurements, in group A, another 13 measurement in group B. Looking at them, it might be challenging, and that is where descriptive statistics come in. If we now find the average, you can see that the average in class A is 110.5, average in class B, 110.23. They are roughly the same, but that would have been difficult by just looking at the data. And this is just 13 students. Imagine if it is 100 or 200, it will make it challenging. So that's where descriptive statistics come. It makes things much easier, to comprehend. Now, the types of descriptive statistics, I said earlier on that for organizing your data and summarizing your data. For the organizing your data, there are two methods. It's either you use tables or graphs. So that is just the summary of descriptive statistics. You organize your data, tables or graphs. You summarize your data, measures of central tendency, measures of dispersion or variation. So for number one, that is organizing your data. For the tables, we can use frequency or percentage distributions, and these are used for categorical or ordinal data. Remember our types of data: categorical or ordinal data, that's nominal or ordinal, as it were, qualitative data. Or we can use it also for continuous data, especially when you put them in groups, when you put them in categories. We can do frequency table, we can do relative frequency, we can do cumulative frequency, and we'll look at all that. For still organizing, we can do graphs, we can do bar chart, we can do histogram or pie chart, we can do a stem and leaf plot, we can do a frequency polygon. Most of these are things I'm sure many of us have already heard about before, but we'll just try and brush through them to remind us and then emphasize some areas that might be of interest. So for tables, I said we can have frequency tables, relative frequency distributions, and then we can have cumulative frequency. So when we say frequency table, it just displays the frequency of various outcomes in a sample. You have, you will have seen that you have your whatever variable that you are talking about, and then you have the frequency here, and whatever it is here, it has a corresponding number of appearance. It provides insight about the data that cannot be quickly obtained by looking at the original data. So these are examples of frequency table. Look at, okay, let me just give this is number 1, this is number 2, number 3, 4, and 5. So you can see number 1, talking about the number of toy cars sold, possibly in a toy supermarket or a toy shop. In January, 20 was sold, in February, 30, down to June, where 35 was sold. It has just summarized, organized everything. The same thing with table 2. It's something about a Likert scale. You can see it's ordinal, very satisfied to very dissatisfied, and the frequency of responses. Look at table 3. Table 3 has an additional column. That's the cumulative frequency. And the cumulative frequency is a very straightforward math. Look at, for number 5, we have 2 frequencies, and that comes out. For number 6, there are 3. Now, we have our cumulative as 5. It's just 3 plus 2, that gives 5. 2 plus 5 gives 7. 2 plus 7 gives 9. On and on like that until we have the total here. It's just an addition, diagonally of the preceding frequency with the present observation to give you the cumulative frequency. And then we have table 4, where it's by tally. And I'm sure you know tally. You start by 1, 2, 3, 4, and if it reaches 5, you cross it, and then you start again. You start again with another tally. Similar to table 5, the number of tallies and the frequency in watts. This is group frequency, which can be used in case your variables are continuous. You can put them in class intervals or categories. So as you can see here, I'm going to 1, 2, 3. I'm putting table 1 for a particular reason, to let you know that table 1 is wrong. If you look at that table very well, you see that we have 15 to 25, 25 to 35. That is a very wrong class interval, because what if you have a particular variable as number 25? Are you going to be putting it here or here? So this ought to have been 26 to 35, 36 to 45, on and on like that, 56 to 65. So I've just brought up that for you to know, so that when you are developing your own group frequency table, you don't make that mistake. But look at table 2, you can see that it has already been implemented there, 10 to 19, 20 to 29, and then we have the frequency table, and the total of observation is 43. Likewise in table 3. Now, I told us earlier on about how we get our cumulative frequency table. Look at this. This is table 1, and this is table 2. In table 1, the number of books read in a month, 2. How many people? 1. And the cumulative frequency, 1. For the second observation, 3 people. The cumulative frequency is now 1 plus 3, like I told us earlier on. You just add this was plus that, and then it gives you this. Likewise, this plus that, it gives you this, and on like that. So we have 12, in all. And it can also be done for a group frequency or class interval. It's just by adding, the preceding frequency with the existing and the observed one to give you the new cumulative frequency. For relative frequency, it's also a very straightforward stuff. In relative frequency, we have the frequency for each observation here. When you add everything, this adds up to 16. So what is the relative frequency of number 1? You just put that 2 over 16, maybe times 100, or you can leave it in decimal. So that is what we have there as 0.125. If you multiply by 100, that's how you get 12.5%. And you can do that for each of the frequency. So relative frequency is just by putting the frequency over the total and multiplying out or dividing it out. It's the same thing that we also have here. The total here is 20. You can see the one here, 5 over 20 or 25%. Likewise here also. That is relative frequency. So we go to graphs. Still talking about organizing our data. We look at graphs. The graphs are, the first one we are looking at is histogram. Like I said, I'm sure you've come across all this before. But the good thing I want to bring out here is that it is used for distributions or data that are measured on interval and ratio level. So this is used for quantitative variables, quantitative. They are like bars, but they don't have space in between them in the graphs. And you cannot use them to display more than one variable. Normally, the variable of interest is placed on the horizontal axis, but there are those that can also be on the vertical. But most of the time, nearly all histograms are the variable of interest are placed on the horizontal axis, and you understand why when we talk about frequency polygon. A rectangle is drawn above each class interval, and the height corresponds to the frequency, the relative frequency, or the percent frequency, depending on your own choice. So this is an example of a histogram. What I want you to see is that all those bars there is no space in between them. It's very important. You can see that they are like matted together. You know, they are like together. There's no space between them, but each bar represents a different distribution. And you can see here, we have the weights, you know, of different people, and then we are having the corresponding, you know, value of each of the bars on the percent level. That is the histogram. This is another example of a histogram for blood pressure. Blood pressure is normally we have the systolic or we have the diastolic. So it's something that you can just like superimpose the two measurements together to save space. So the one on top is systolic, the one below is diastolic, you know, and you can see that it's still not having spaces in between them. This is another one, the weight of students, and we have here the class intervals and then the corresponding frequency. We also have another one here, histogram, you know, but this one is showing what we call a symmetric shape. And you'll have heard of that name. They say it's bell-shaped. So you can see. Sorry. I want to draw that line that makes it look symmetrical. Something like that. It's bell-shaped. So this particular histogram is symmetric. You know, the left side mirrors the right side. And an example is the weight or height of people. When you take a random sample of people, take their weight and height, you normally have something like this. It's a normal distribution. This one is skewed to the left. You will see that the left side seems to be longer compared to the right side. We call it a left skew. And then we have a right skew here also. The right side tends to be longer, you know, compared to the left side. And we can even have the one that there's a high skewed to the right. You know, it's very long, you know, and you understand this as we continue about the different, what's it called, shapes of histogram. So the skewness is actually a measure of the asymmetry of a distribution. The one that is symmetrical, the skewness is 0. That is where the left side mirrors the right side. The positive skewness, we have a long right tail, like I showed us. The negative skewness, we have a long left tail. When you do your analysis and you draw, you do a histogram, you can describe your histogram by saying it's either symmetrical or there's a positive skew or a negative skew. So these are shapes of histogram. Okay, let me give them 1, 2, 3, 4, 5, 6. Number 1 is symmetrical. You can see that the left side is similar to the right side. Number 2 has a right skew. It has a longer slope on the right. And number 3 has a left skew, a longer slope on the left. Number 4 is also symmetrical, but there's something unique. It is peaked. You can see that it has like it's peaked, unlike this one that is more like, not too peaked, but a bit more beveled. But number 5 is more like flat, although it's symmetrical, but it's flatter. We'll talk about that. And number 6 is bimodal. That means it has 2 different peaks. It's also called, not a uniform, a U-shaped. Yeah, it's also called a U-shaped histogram, bimodal or a U-shaped histogram. This one that is peaked is called leptocotic, and the one that is flat here is called platycotic. We'll get there now. Just let's continue. So kurtosis is a measure of the extent to which the observations cluster around a central point. So this particular number 4 is a measure of kurtosis. You can see that the values are closer to the center. That's why it is peaked, you know, and it's also the one applying to number 5. They are all measures of kurtosis. So the leptocotic data are more peaked, while the platycotic values are flatter and they are more dispersed. Okay, so we have number 4, the leptocotic, and number 5, the platycotic. Flat is flatter when you have your distribution. A bar chart is another type of graph you use to organize your data, and this one is used for nominal and ordinal data. You can see why the emphasis to know the type of data you collect. A single bar chart can present 2 or more presentations. They have spaces between them, unlike the histogram. Remember, the histogram is matted together, the bars have no spaces, but the bar chart have spaces between them. They are separated to emphasize the fact that they are in categories. Remember categorical variables. And the height is proportional to the frequency, or percentage of each category. So look at an example here. We have bar chart here. We have for men, we have for women. And you can see the key. The blue one says British home student. The red one says international student. So it looks like maybe a kind of classification of students in a particular school, those that are home-based students and those that are international students. So for 2010, for the men, the blue, that is around 39, are more than the international students, which is around 20. And you have them categorized like that, separately for men, separately for women. This is another example of a bar chart, and here it is combining two variables, one here, the other here, just to make it look beautiful. Look at another bar chart here. It comes in different designs, different shapes. It can be on vertical axis, it can be on the horizontal axis, like this one is going horizontal. And it's just the fact that there are spaces in between the bars. That is the easiest way to identify that it's a bar chart, unlike a histogram. This is an example of a Pareto diagram. And it's nothing, highfalutin is a very simple chart. Number one, it has a bar chart component, which you can see, A, B, C, D, E, F. That's a bar chart component. How do we know? We can see that there are spaces in between them. What is this particular line? This is just the cumulative frequency. Remember your table, your frequency table. So for A, there's going to be a cumulative frequency. For B, the cumulative frequency. So it's just a line chart on top of a bar graph. That's what we call a Pareto diagram. It looks beautiful. It looks a bit scientific, but there's really nothing there. You can see that for the cumulative frequency, it has its own vertical axis here. And for the bar chart, there's its own frequency axis here. So it's just a combination graph having a cumulative frequency and then the frequency of observations together. That is a Pareto diagram. A pie chart is similar to a bar chart because it's also used for a nominal or ordinal data because they are in categories. You can give different colors to the different sheets or segments of a cycle to differentiate one category from the other. We normally use it to describe a single distribution, but you can use it to compare like two or more. You first have your cycle drawn, and then you use your relative frequency to subdivide the cycle into corresponding sectors. You have done this before. It's just a reminder. We don't need to go into the details of how a pie chart is done, but the fact that I'm just trying to bring out here is the fact that it's used for nominal or ordinal data. So this is an example of a pie chart. And just looking at this pie chart without even much explanation, we can say that Australia has the lowest frequency while Germany has the highest. As simple as that, it has organized your data. This is a comparison, and they are both the same variables, but two different years. We can say, okay, like in 1998, you can see here that green, our green is Italy. Italy has 11.8%, and in 2007, it has 11.9%. So we can, from these graphs, this chart, look and say that there's been a 0.1% increase in the population of Spain and of Italy because it is the green color. When we look at the blue color, that is France. In 1998, it was 12.5. In 2007, 12.8. So just looking at this, it has brought about a clarity and summarizing the data for, organizing the data for comprehension. And these are just different examples. You can have a pie chart and then a combination bar chart. They actually measure the same thing, ordinal and categorical data, ordinal and nominal data. And it can also be in this design where it's more like a donut. It's still saying the same thing, and we have all the percentages like superimposed upon the different segments for us to see. So this is an example of what I've been talking about, especially with organizing data. I'm talking about a fast food joint, Mr. Biggs, which many of us must have been conversant with. So customers visiting Mr. Biggs, they were asked to rate the quality of their experience as either being excellent, above average, average, below average, or poor. And if you look at this measurement, it's an ordinal measurement because it's going up, or it can bring it down also. And for 20 customers, these are the measurements, below average, down to average, plenty. And this is just 20. So imagine if it is for 200, it can be so challenging. Now, the frequency distribution, those who said poor from that previous data, is only 2. And those who have below average 3, average 5, above average 9, and only one person said what's it called? Excellent. From the way it is now, you can actually calculate your cumulative frequency. Like I told you, this is going to be 2, the next one is going to be 5, this is going to be 10, this is going to be 19, and the last one is going to be 20. One thing you must put in mind is that your final cumulative frequency must agree with your total frequency, and that's how you know if you are right. So that's your cumulative frequency, okay? And then we can now find the percent of the frequency, which is your relative frequency. How did we get this 0.10? It's 2 over 20. Remember, let me just go back. Our frequency here is 2. Divided by 20, it will give you 0.1, which is what we have here. And on like that for your relative frequency. And you can multiply them by 100 to have your percent frequency, which is what you have here. You can convert this to a bar chart, is what we are seeing here. And clearly now, we can tell you without much ado that people with above average are more. That's 9, you know, and the list is excellent, which is just 1 person. That is what a bar graph will give you. Just one look, and you can see a summary of what we are talking about. Likewise, for the pie chart, which is similar to the bar graph, we can see that above average is far close to like half of the population, and only 1 person said excellent. And half, a quarter said average. That's 5. That's 25%. That's the pie chart for you. A stem and leaf plot is another way to organize your data. A stem and leaf plot is a special table where each data value is split into a stem, and that's the first digit or digits, depending on the number, and a leaf, which is usually the last digit. So let me start from this particular one here. We have a stem, and this is the number that we are trying to create a stem and leaf plot for. 15 down to 41. So what you do is you pick the first number, which is 1, 2, 3, and 4. And then you arrange the next numbers in front of them. They are the leaf. So this is number 16. This is number 26. The first one, 26, the second one. And then you arrange it like that. Look at this particular one now. Now it is 120 to 129. So you can see that number 1, 2 is common to all the numbers. That's why we have 12 alone as the stem. And then 0 to 9 are arranged as the leaf. You know, 0, 1, 2, 3, 4, 2. Okay, this is supposed to be 9 because the last number there is 9. So that's a stem and leaf. Very simple way to just organize your data. It doesn't have any serious calculation. Arrange the data in order in making a stem and leaf. Separate the data according to the first digit or digits, depending on, you know, the numbers, and make a display by using the leading digit as the stem and the trailing digit as the leaf. So we have another one here. This is number 36. This is number 53. This is number 10. It's just by looking at the initial stem and adding it up to the digits there, you know. And this is a key in case you are using such a method to show how to read the diagram. Okay. For number 6, because it is starting with a single unit, that's why we have 0 here. That's why that one is number 6. 0, 6 is the same thing as 6. And even from this particular stem and leaf, you can actually look at the stem and leaf and tell us the particular number that is commonest. I will tell you is number 17 because it's the only number appearing 3 times. As simple as that. That's the stem and leaf for you. And this one is a classwork which I want you to do at your convenience. I'll be sharing the slide with you immediately after this class. You just arrange it like I've said, and then you check and make a stem and a leaf for that. A frequency polygon is a graphical device for understanding the shape of distribution. So we were talking about histogram earlier on. It's a frequency polygon that makes us to know how the shape is. They serve the same purpose as histogram, but they are better and they are most especially used for comparing data sets. So they are also a good device for displaying cumulative frequency of data sets. So we have histogram here. This one, that is this is number 1 here, and this is number 2. There's something I want you to notice. Look at the histogram on chart 1. You will notice that there's a line connecting the midpoint of the histogram. That's the top of the histogram. And that line goes up and comes down. Look at graph 2 also. From the midpoint of A to the midpoint of B, midpoint of C. on and on like that. So that line that connects the midpoint and which your computer can do for you is what we call a frequency polygon. It gives you an idea of the shape of that histogram. Look at this one. These are examination mark. And you can see that it's having like a dome-shaped appearance. That's frequency polygon. Now you can remove the background histogram and all you have is just the line. So this is a frequency polygon, showing you the distribution of a particular data set. This is another one, and then you can have two different frequency polygons superimposed on each other, just for comparison's sake. The large target here, the small target here, you can see that there's a difference. That's frequency polygon. We have another kind of way to organize our data, which we call a dot plot. It's a graphical display and it's used to show data distribution. And they are used for univariate data. Remember, I mentioned that earlier on, when the variable is either categorical or quantitative. So it can take the form of a bar graph or histogram. And the bar graph is the Cleveland, the histogram is the Wilkinson. And I'm going to show you. The bar graph is the Cleveland, the histogram is the Wilkinson design. So this is an example here. The number of books read last summer. So these are the number of books, that's the Cleveland. You can see that there's like a space in between each dot arrangement. That is the bar type of the dot plot. So from this particular graph here, I can say that the number of books read is the highest one is 1, that people read last summer. 6 people read only 1. Others are less than 1 in frequency. So that is the Cleveland type of dot plot. And the other type of dot plot is the Wilkinson, where it simulates the histogram. So here it's something that one can actually join like with a line to give an impression of how it is. But it doesn't have to have a line anyway, because putting a line makes it a line chart. It differs. But the plot with what's it called? With the dot alone, that makes it the Wilkinson dot plot. That's another way, to express or to summarize and to organize your data. This is another example of Cleveland and another example of Wilkinson. Both of them are dot plots. So the line chart or line graph, or also known as curve chart, you can say it has synonyms, is a type of chart that displays information as a series of data points called markers, and it's connected by a straight line segment. It's actually a kind of chart that works with serial time. That's a time series. It has to do with timing. Something happened at a particular time, at another time you have another measurement, on and on like that, and then you are joining those measurements together to give you, an organized way of understanding what has happened. That's a line chart, and these are examples of line charts. And that's another example of line chart. The frequency of students part-time and full-time. You can see that we have a time series here talking about the year. Now, there's a similar type of chart, which is the time series plot. While both line chart and time series plot are used to visualize data over time, both of them are used to visualize data over time. A time series plot is a specific type of line chart where the horizontal axis represents time. The horizontal axis represents time. That's the x-axis. That one is specific. It is time that is always there. That means that for the line chart, the vertical axis can also represent time, depending on how you want to arrange it. But in the, what's it called? In the time series plot, the horizontal axis represents time. So this is an example of a time series plot. You can see the horizontal axis starting from the year 1880 down to 2020, and then all those different markings are joined by a line to just show that there's something happening over time in that particular reading. So for descriptive statistics, we have it that you can organize your data, which we have discussed, either by tables or graphs. Then the other option is summarize your data, which is the measures of central tendency or the measures of variation. So for the summarizing of your data, it's normally done with quantitative data, which have the measurement scale of either interval or ratio scale. Quantitative data, QT. So for the central tendency, it's mean, median, mode. For the variation, it is range, interquartile range, variance, and standard deviation. The mean is something we all know is just an average. You add all the numbers by the total frequency, and you have your mean. I'm not going to spend much time there. This is an example, like we saw earlier in the presentation, class A, 13 students, class B. We add all the figures of the weights together and divide by 13 to give us that. All the figures divided by 13 to give us that. That is how we got the mean. Now, this is where I want us to pay some attention. The mean is good when you are trying to make inferences to the population itself. That is inferential statistics. And the mean is not very resistant to outliers. What's an outlier? A thing or a person that is far detached from the main body or system. Like I will give an example in the next slide. Maybe all of us, we look at our monthly income, and then we want to compare it with that of maybe Dangote or Warren Buffett. Warren Buffett or Dangote is an outlier because they are not in our level. They are far, far detached. So when you have data sets that has outliers, you don't use a mean to describe your data. Please don't forget that. When you have data set that has an outlier, you don't use a mean to describe your data because it will skew your data. So this is an example. Means can be badly affected by outliers. Okay, outliers can make the data a bad measure of central tendency. Why? Because they will skew the data. Income in our group, you can see that we have a very long skew. Look at where Dangote is. It has skewed data. It's not going to be a good representation of what we have. So let's assume that all of us are earning $5,000. There are those earning 7, there are those earning 6, there are those earning maybe 8, thereabouts. And then we now have somebody earning like $1 billion. By the time you want to find the average, it's going to give us a wrong impression. That's all I'm trying to say. It will now bring everybody towards the area of the skew as if we are all rich. Whereas our income is different from the total. So that's why you don't use a mean when you have an outlier in your data set. This is what I'm talking about. You can see here we have many people here, and we only have 3 people here. And these 3 people, by the time we add, we have an average of 70. So it has skewed, the distribution. It has skewed the distribution. If your frequency distribution shows outliers, you might want to use a median instead of the mean. So please don't forget that. Don't use a mean if you have an outlier in your data set. So the properties of the mean, it's best known measure of central location or central tendency. The good thing is that all the data are involved when you are calculating the mean because you have to add everything and then divide by the number. But it is affected by outliers, and the mean is best for normally distributed data. Normally distributed data. It's not usually equal to one of the original values, but it has good statistical properties. And in research, you normally see it being represented by mean plus or minus standard deviation. Okay? The median is the middle value. When your values are ranked in order, either ascending or descending, you just pick the middle number. When it is like even number, you pick the 2 numbers in between and you divide it by 2. And the median is also called the 50th percentile. So we have a class of 13 students. You have arranged them from ascending to descending. This is number 109. That's the weight, that's the median. It's as simple as that. Now let's assume this number 89 is removed. We now have 12 of them. So you now have to pick the 2 that are in the middle. You now have to pick the 2 that are in the middle. That is 109 plus 110 and divide by 2 to give you the new median, which is 109.5. Okay. The median is unaffected by outliers. So even if we have somebody who has a very weird measurement, the median does not use all those outliers in its calculation. It's just the middle factor. So it's better describing the typical person, than the mean if you have a skewed data. So when you have a skewed data, just work with the median. The median is the better representation of this measure of central tendency. If the recorded values for a variable form a symmetric distribution, both the mean, the median, and even the mode are going to be identical. So in skewed data, the mean lies further towards the skew, but the median is closer, towards the middle. So we have that same example. You can see our median. So the median income is $30,000. The median income is $30,000. It doesn't affect if we have somebody having $710,000 annually. We have the median there. And the properties of the median, it does not use all the data. and it's not sensitive to outliers. It's a good measure, but it has poor statistical properties. And like I kept saying, it's the measure of choice for your skewed data. Please don't forget this. When you have a skewed data, you use a median. The mode, like we said, is the commonest occurring maybe data or observation rather. The commonest occurring observation. Look at this. When we combine class A and class 2 together and we arrange them in ascending order, number 109 is occurring like 3 times, so it's the mode. And it's possible you have more than one mode. Look at this particular one on top. There's no mode because all the observations are appearing once. But for the second example, number 3 is the mode. It's appearing 3 times. And in this example, we have 2 and 5 appearing at the same frequency. So both of them are mode. So this is a bimodal, frequency, bimodal. The mode will give you the most likely experience rather than the typical. The typical is the median. The central is the mean. In symmetric distributions, like I said earlier on, the mean, the median, the mode all happen to fall on the same time. And in a skewed data, both the mean and median, they lie further away towards the side of the skew, unlike the mode. See it here again. This is the mode, is the commonest appearance. That is $20,000 annually. The median and the mean, they lie. So let me just do a skew. This is a very long skew. Both the median and the mean lie towards the side of the skew. The mode is the commonest presentation. So in a normal distribution, mean, median, and mode are the same in a normal distribution, okay? So we've discussed measures of central tendency. Let's look at variation very fast. Variation number 1 is range. The range is just the distance or the difference between the highest number and the lowest number. So in class A here, the highest rate is 140, the lowest rate is 89. The range is 140 minus 89, 51. In class B here, the highest rate is 162, the lowest is 89. The range is just 162. It's just 162 minus 80, which is 82. That is the range. The range is very straightforward. Interquartile range is the value that marks one of the divisions and breaks a series of values into 4 equal parts, like a quarter. A quarter is like one fourth of a whole. The median is a quartile and divides the cases into half. So we have the 50th percentile, that is the median. Okay, the 25th percentile is a quarter that divides the first 1/4 of the cases from the latter 3/4. That is the 25th percentile. This is the 50th percentile. This is the 75th percentile. It divides the first 3/4 from the latter 1/4. So when we talk of interquartile range, it's just the value of Q3 minus Q1. That is interquartile range. Please don't forget that. Interquartile range is the value of Q3 minus Q1. And when you are doing this, it's best you arrange your numbers in ascending orders. You arrange your numbers in ascending orders from the lowest down to the highest, and then you can pick it. You can just use the simple method of median to pick the 50th percentile, and then the remaining 2 sides, 50-50 side, you'll find the 25-25, which is the middle again of the remaining 2 numbers. So the interquartile range is the distance between the 25th and the 75th. That is Q1 and Q3. Look at this box plot below here. We have the upper quarter here. This is Q3. And we have the lower quarter here. This is Q1. Our Q1 here is 4. Our Q3 here is 15. Our interquartile range is just 15 minus 4. That is 11. It's as simple as that. And our Q2 here should be like maybe 10.5, somewhere around here. So it's a very straightforward process. There's really nothing cumbersome about that. So this is an example that you are still going to do. We'll look at them next when we meet the next time. We have 12 students who are examining to see the number of push-ups they can do after a plate of food. So we have the readings here. You are going to find the 3 quartiles, that is Q1, Q2, and Q3. And then you find the semi-interquartile range. So you just arrange these numbers in ascending orders. You can start by finding the Q2, you put that down, and then on the left side of Q2, you can find the median. On the right side of Q2, you can find the median. And those median will be Q1 and Q3, and then you can find the semi-interquartile range. So you just do that for us to see if we are following. Variance is a measure of spread. if you look at these two histogram of frequency polygon, this one is like platychotic, this one is like lepto, remember the measurements. So it's a measure of spread or dispersion. The larger the variance, the further the individual cases are from the mean. The smaller the variance, the closer they are to the mean. They are like clustered together to the mean. Consider these numbers: 5555, 13894, 44449, 55645. If you find the mean of all these numbers, the mean of all these numbers are 5555, but they are different figures forming that 5. So there are those that vary. Like this particular one is going to have like a variance, unlike the first one that is a constant. This one is a constant. They all have the same figure. Look at this particular class now, class A. Our mean is 110.54. We want to look at how far apart are these numbers from the mean. So we look at how far apart 102 is away from 110.54 and all the numbers individually. And the interesting thing is that if you find the deviation from the mean and you add up their deviation, you will have those that are positive, those that are negative. By the time you add everything together, it will give you 0. So let's just continue. You'll see what I'm talking about. So the deviation of 102 from the mean is minus 8.54. The deviation of 115 from the mean is plus 4.46. If you are to add up all the deviations of all the individual weights, you will end up with negative. Why? Because the positive will knock up the negative, and then you have 0. Sorry, you end up with 0, because positive will eliminate negative. And to be able to understand the variance, we now square those deviations. For example, that deviation of 102 from the mean, which we have as minus 8.54, we square it to give us 72.93. The one of 115 from the mean, which is 4.46, we square it to give us 19.96. So we can now add all those deviations, the squared values, for us to have a figure, and then what we have when we add everything is what we call the sum of squares, which you are going to see here. So you can see each of the particular weight had been, taken away from the mean. And by the time we find the squared value of the deviations, we have 2,825.39. That's for each of those 13 students. Now, the next step is to look at the average variance or dispersion from the mean. And there's a formula for that. It's just the sum of squared divided by the number in the population, or if it's a sample that you took, your sample minus 1. And most of the time, like I said, we work with sample size. So it's going to be the sum of squared divided by the sample minus 1. And that is the formula we have here. This formula, that's the formula for variance. By the time you do that, our sample is 13. 13 minus y is 12. So that's the sum of squared divided by 12. And that's the value we have. So the question is, how helpful is that? It doesn't really have any meaning because our unit of the variance is squared. How do we interpret that? So that is the what takes us to the next step. So if you are told to calculate the variance, that is the variance for you. But variance has no interpretation. So we need to go a step further by calculating what we call the standard deviation. And standard deviation is just finding the square root of the variance. As simple as that. A standard deviation is just the square root of the variance. So that is just the formula. It's just the square root of the previous formula that we have here. So once we have a square root over that, that gives us the standard deviation. So by finding the square root of 235.45, we have 15.34. That is our standard deviation. So that standard deviation is just the average deviation from the mean of the different people's scores. Average deviation. We have those that are higher, we have those that are lower, but the average deviation or dispersion from the mean is 15.34. The larger the standard deviation around the mean, the flatter the distribution. So if you have a leptochotic histogram or distribution, that shows that the standard deviation is close to the mean. But if you have something that is flatter like this, it shows that the standard deviation is further away from the mean, even if both of them have the same value. Like the mean, the standard variation and standard deviation is also inflated by an outlier case. So when we have, let's say our mean is 41 plus or minus 3, that shows that most of them are close to 41. Our mean is 41. Most of the values are close to 41. But let's say we have 41 plus or minus, like maybe 27. It shows that there's a kind of broad distribution of the figures. Now, let's say we have 41 plus or minus 50. This already is above the mean, and that shows that there is an outlier in your variable, and you shouldn't be using a mean to describe your data. Please don't forget that. The moment you see that your standard deviation is more than your mean, it shows that there's an outlier somewhere, and you shouldn't be using a mean to describe your data. Rather, you work with a median. So this is an assignment for you. You calculate the variance of all these numbers, and then you calculate the standard deviation, and then we'll discuss them briefly when next we meet. Please don't forget that assignment number 3. I'm sharing the slides once I'm done. You will understand what I'm talking about from this slide. So look at this example here. There are two classes, class A and B, and both of them have the same mean of 80, but they have different standard deviation. How do you interpret that for you that you'll be reading articles? So we have the mean of 80. Class A has a standard deviation of 5. Class B has a standard deviation of 15.8. So what it means is that for class A that has a standard deviation of 5, most of the scores are close to each other. So all the students are more or less like of the same level of IQ, if I can use that term. But for class B, there are those that have 60, there are those that have 100. It's more dispersed. That's why the standard deviation is bigger. That's how you interpret those figures. If you see anything mean plus or minus standard deviation, it gives you an idea of how to interpret the main data set itself. Like I said, if your standard deviation is greater than your mean, that means you have an outlier, and the mean is not the best way to summarize your data. So we've discussed range, interquartile range, variance, and standard deviation. So let's just look at the last, what's it called? The last example, and that's the box plot. It's a way to graphically portray almost all the descriptive statistics at once in the box. The box plot will show you the upper and lower quartile, that is Q3 and Q1. It will show you the mean, median, and range. And it will also show you outliers. Outlier is 1.5 of the interquartile range plus either the Q1 or the Q3. Okay, these are examples of how box plots look, in case you come across them. This is the box plot. They are also called whisker plots. When you see a dot either above or below, those dots are outliers. In the normal distribution, they are outliers. This is another example. This is another example of a box plot, and this is just the interpretation. Like I said, that dot is an outlier. This upper part is the maximum reading, and in the box, the upper part here is the Q3. The median is the Q2, the lower quartile is the Q1. So you can actually calculate, the interquartile range, just looking at the box plot. And the lower part of the whisker is the minimum. So this is just the interpretation of a box plot. Box plots, they have box from lower quartile to upper quartile, which is straightforward, with the median marked in the middle, and they portray a 5-number summary. The minimum, the lower quartile, the median, the upper quartile, the maximum. This one also has an outlier here. So how do we know what an outlier is? If it is above the Q3, this is the Q3, any figure that is 1.5 of the interquartile range, which you can calculate, added to the upper quartile, any figure above that is an outlier. And any figure below 1.5 of the interquartile range removed from the lower quartile is also an outlier. So you can have an outlier somewhere here also, as long as it's either below this figure or above this figure. So if our lower quartile is 2, upper quartile is 10, and our interquartile range is 8, 1.5 of interquartile range, is 11. sorry, 1.5 of interquartal ridge, that is plus the upper quarter giving us 22 is already an evidence that that number is an outlier. And likewise, if we are going to remove this figure from the lower quarter, if it's possible, maybe having a negative, it is also going to be an outlier. So the computer will automatically generate this for you to see, there's an outlier. This is all I've been talking about. This is the minimum, this is the maximum, this is Q3, this is Q2, this is Q1. All these ones, because they are beneath the lower quartile and they are above the upper quartile, they are all outliers. So now I think we are qualified to use descriptive statistics. I apologize. I was hoping I was going to be able to maybe stop 5 minutes before time to just do a sample analysis on SPSS, but that we can do in our next class, maybe in the first 10 minutes. We'll do the first 5 minutes, we'll do that in our next class and look at our assignment also, But if you were to do an analysis on a variable, let's assume that you have maybe a variable age and you have collected the data for age, you tend to see something like this for a descriptive statistics, because your software will give you the mean, it will give you the standard error, the median, the mode. You understand what the standard deviation is, you know what the variance is by now, you know what the kurtosis is, you know skewness, you know range, you have minimum, maximum, you have sum, you have count. So all I'm trying to say is that by now, if you see an output like this from a software, from a statistical software, you should be able to understand, what it means. For the kurtosis and skewness, all this is just to show that this is close to normal. Remember, both of them are supposed to be 0, 0 for a normal distribution, but because they are not 0 on the dot, it's just a slight, deviation in either the peakness of this distribution or the skewness of the distribution. I think I will just stop here. I've exceeded my time. I apologize for that, but I have, I think I'll be able to take 1 or 2 questions before we round up. Dr. Lawal, please, over to you.
Thank you very much. I mean, this is statistics made ridiculously simple. That's just a summary of what we had this morning. Thanks for the continuous teaching and teaching in a way that people can really understand. We really appreciate that. So we'll take 1 or 2 questions, then we'll wrap up today. Any question?
Thank you once again, my prof. I'm sure while we wait for questions, I just want to highlight, of course, when you're in this class, there's always something to learn. But just to highlight something that I heard, and I think it's very important for you to take away, which often you hear in class or some way when you're in school, that when you have outliers, you delete the outliers. Please hear it very, very well. When you have outliers, you choose the right statistical tool to deal with it. You are not expected to delete any data from your data set as long as you have collected it appropriately. Otherwise, you start to tamper with the true value of what you found. I repeat again, once you have collected your data, you would clean. Your cleaning doesn't say you delete data. You look for what is appropriate and address anything. And when you want to analyze, you do not delete outliers. You choose the appropriate tool to be able to manage your data. Thank you very much once again, and over to you, Dr. Lawal. Yeah, if there's any.
Yeah, thank you very much for that, Prof. So I think all I can see is a comment appreciating the simplicity of the training. Prof has broken it so much into bits that everybody understood what was taught. So what I would advise the fellows to do is to bookmark this YouTube link and watch it repeatedly. You can't have it taught better than this. Thank you very much, Prof.
Thank you, Dr. Lawal. So I'll be sharing a copy of the slide with you immediately after now, and you can help him broadcast to the participants here.
All right, thank you, sir. Yeah, so IT, you can stop live streaming and the fellows can go have their weekend. The TAs and the faculty will have a short meeting thereafter.
Thank you, everyone. Maybe